In the early hours of October 19th, 2017, a faint moving object was recorded in a sequence of wide-field images taken from Haleakala Observatory in Hawaii. The detection did not come from a human observer, but from an automated survey system designed to identify transient and moving sources in the night sky. The telescope responsible was Pan-STARRS, one of the most advanced near-Earth object survey instruments operating at the time. Pan-STARRS continuously scans large regions of the sky using high-resolution digital imaging. Each night it collects massive datasets and compares new images with earlier observations. Stationary objects, stars, galaxies, and nebulae are mathematically removed through a process known as difference imaging. What remains are objects that change position or brightness, asteroids, comets, artificial satellites, and various sources of noise. Most detections fall into well-understood categories and are processed automatically with minimal human involvement. The object detected on October 19th initially appeared unremarkable. It was faint, near magnitude 20, and showed a slow, apparent motion consistent with a small body passing through the inner solar system. The automated pipeline flagged it as a moving source, assigned a temporary identifier, and forwarded it for routine orbital analysis. At this stage, there was no indication that the object was unusual. As additional observations were obtained over the following nights, astronomers began calculating a preliminary orbit. This process involves fitting the observed sky positions of the object to classical gravitational dynamics to determine its trajectory around the Sun. Almost all known small bodies in the solar system follow bound orbits, ellipses with eccentricities less than 1, meaning they are gravitationally tied to the Sun. Some objects, particularly long-period comets originating from the distant Oort cloud, approach eccentricities very close to 1. These objects are only weakly bound and may take millions of years to return after passing through the inner solar system. However, even these extreme cases remain technically bound. The new object did not. Early orbital solutions indicated an eccentricity clearly greater than 1. This value did not merely approach the threshold between bound and unbound motion. It exceeded it by a statistically significant margin. An eccentricity above 1 corresponds to a hyperbolic trajectory, meaning the object is not gravitationally bound to the Sun and will pass through the solar system only once. Because early orbital fits can be unreliable when based on limited data, astronomers treated this result with caution. Measurement uncertainties, especially for faint objects, can sometimes produce artificially hyperbolic solutions that later resolve into ordinary elliptical orbits as more data become available. This has occurred many times in past surveys. For this reason, rapid follow-up observations were prioritized. As the observational arc lengthened, the orbit became better constrained. Each new measurement reduced uncertainty in the trajectory. Crucially, the eccentricity remained above 1 even after accounting for observational errors, planetary perturbations, and solar radiation pressure. The hyperbolic nature of the orbit persisted. At this point, the object was provisionally classified as a comet, which was standard practice for fast-moving bodies detected far from the Sun. However, this classification soon became problematic. As the object approached perihelion, it showed no evidence of cometary activity. High-resolution imaging revealed no dust coma or tail. Spectroscopic observations failed to detect common volatile gases such as water vapor, carbon monoxide, or carbon dioxide. Despite its proximity to the Sun, the object behaved like an inert body. This raised the possibility that it was an asteroid. However, asteroids are overwhelmingly confined to bound solar system populations such as the main belt, the Kuiper belt, or near-Earth space. Their orbital energies and velocity distributions are well characterized, shaped by billions of years of gravitational interactions within the solar system. The incoming velocity of this object, calculated before it encountered the Sun's gravitational influence, did not match those distributions. There was no plausible interaction with any planet that could have placed a native solar system object onto such a trajectory. In particular, gravitational scattering by Jupiter, a common mechanism for ejecting objects, could not explain the observed motion without leaving clear dynamical signatures which were absent. The object was not being expelled from the solar system. It was arriving already unbound. This distinction was decisive. Objects scattered outward by planets acquire hyperbolic trajectories only after close encounters. In contrast, this object approached the Sun on a hyperbolic path from the outset, indicating that it originated beyond the solar system. By October 25, 2017, the conclusion was unavoidable. The object was interstellar in origin. It was subsequently designated Oumuamua, becoming the first observed member of a new class of astronomical objects, interstellar small bodies passing through the solar system. The designation 1I explicitly marked it as the first such detection. Importantly, Oumuamua was discovered after it had already passed its closest point to the Sun. It had approached from a direction close to the Sun's position in the sky, a region poorly covered by ground-based surveys due to daylight interference. Only after it moved into darker skies was it detectable by pan-stars. This geometry explains why it was detected late and carries broader implications. If one interstellar object passed through the inner solar system and was detected only after perihelion, many others may pass through undetected. Early population estimates suggested that objects like Oumuamua could traverse the solar system regularly, with only a small fraction being observable given current survey limitations. The discovery did not rely on unusual technology or targeted searches for interstellar visitors. It resulted from routine sky monitoring combined with precise orbital analysis. A small deviation from expected motion was enough to reveal that material from another star system had entered the Sun's gravitational domain. For the first time, interstellar space was no longer an abstract source of theoretical debris. It had delivered an object that could be measured, tracked, and studied briefly before continuing on its path back into the galaxy. Once the possibility of an interstellar origin was raised, the question shifted from detection to proof. Extraordinary claims in astronomy do not survive on suggestion or intuition, they stand or fall on orbital mechanics. For Oumuamua, this meant reconstructing its trajectory with enough precision to rule out every plausible solar system explanation. Orbit determination begins with astrometry, precise measurements of an object's position on the sky at specific times. Each observation contributes a point, and together these points define a trajectory governed by gravity. For nearby fast-moving objects, even small positional errors can translate into large uncertainties in orbital parameters. This is why early solutions are treated cautiously, especially when based on short observational arcs. In the case of Oumuamua, follow-up observations were rapidly obtained from multiple observatories worldwide. These measurements extended the observational arc from a few days to several weeks, dramatically improving the accuracy of the orbit. As the dataset grew, standard least squares fitting techniques were applied to solve for the object's orbital elements under Newtonian gravity, with relativistic corrections included where necessary. Each iteration reduced uncertainty. Critically, the eccentricity did not drift toward 1, as would be expected if early measurements had been misleading. Instead, it converged on a value of approximately 1.2. This value lies well beyond the error bars and far beyond the regime of weakly bound solar system objects. In orbital mechanics, eccentricity defines the shape of a trajectory. Values less than 1 correspond to ellipses, which are closed orbits. An object on such a path remains gravitationally bound to the Sun. An eccentricity equal to 1 describes a parabola, the exact boundary between bound and unbound motion. Values greater than 1 describe hyperbolas, open trajectories that carry objects through the solar system only once. Oumuamua's eccentricity was not marginally hyperbolic, it was decisively so. Another crucial parameter was its velocity at infinity. This quantity represents the object's speed relative to the Sun after subtracting the Sun's gravitational influence. In practical terms, it is the speed the object had before entering the solar system, far from the Sun, where solar gravity becomes negligible. For Oumuamua, this velocity was measured to be on the order of 26 kilometers per second relative to the Sun. This is not an arbitrary number. It is comparable to the Sun's motion relative to nearby stars in the Milky Way, placing Oumuamua's motion close to the local standard of rest. This alone carried important implications. Objects ejected from the solar system by planetary encounters typically leave with velocities close to zero at infinity. They gain just enough energy during a close gravitational interaction to escape the Sun's pull. Their hyperbolicity is acquired, not intrinsic. As a result, their incoming velocity before the encounter is always consistent with a bound orbit. Oumuamua did not fit this pattern. Its incoming velocity was non-zero and substantial, indicating that it was already travelling through interstellar space before encountering the Sun. There was no evidence of a recent gravitational slingshot event involving Jupiter, Saturn, or any other planet. Such encounters leave clear dynamical signatures, including characteristic changes in trajectory that were not observed. This ruled out planetary scattering as an explanation. Another possibility considered was that Oumuamua originated in the distant Oort cloud, the vast reservoir of icy bodies surrounding the solar system at distances of tens of thousands of astronomical units. Long-period comets originate from this region and often enter the inner solar system on nearly parabolic orbits. However, nearly parabolic is not the same as hyperbolic. Even the most weakly bound Oort cloud comets have eccentricities slightly below 1. In rare cases, passing stars or galactic tides can perturb these orbits, nudging them closer to the escape threshold. But producing an eccentricity as large as Oumuamua's through such processes would require an extreme and finely tuned interaction for which there was no evidence. Moreover, Oort cloud comets approach the Sun from an isotropic distribution of directions. Their velocities at infinity cluster near zero. Oumuamua's velocity and direction were inconsistent with this population. It did not behave like an object loosely attached to the solar system's gravitational fringe. There was also the question of non-gravitational forces. Small bodies can experience subtle accelerations due to outgassing, radiation pressure, or thermal effects. If unaccounted for, these forces can bias orbital fits and artificially inflate eccentricity estimates. For this reason, astronomers tested models that included additional acceleration terms. Even under conservative assumptions, the hyperbolic nature of the orbit persisted. While non-gravitational acceleration would later become a topic of intense study, it could not erase the object's interstellar signature. In other words, even if Oumuamua had behaved like a weakly active comet, its trajectory would still require an origin beyond the solar system. Comparisons with known long-period comets further reinforced this conclusion. When their orbits are reconstructed with modern data, even dynamically new comets from the Oort cloud show velocities at infinity consistent with bound motion. Their hyperbolicity, when present, is slight and often disappears once observational uncertainties are fully accounted for. Oumuamua stood apart. Its orbit was not only hyperbolic, but robustly so. Independent analyses by multiple research groups using different datasets and methods converged on the same result. The agreement was not marginal, it was decisive. This level of consistency matters. Orbital solutions can be sensitive to assumptions and data selection, especially for faint objects. In this case, however, the conclusion survived repeated scrutiny. There was no plausible solar system reservoir capable of producing an object with Oumuamua's trajectory without invoking ad hoc scenarios unsupported by evidence. By late October 2017, orbital mechanics had done what speculation could not. It had closed the door on a solar system origin. The object was not a comet thrown inward from the Oort cloud. It was not an asteroid ejected by planetary interactions. It was not a fragment of a recent collision within the solar system. It was a visitor. This realization carried broader consequences. For decades, models of planet formation had predicted that young planetary systems should eject enormous numbers of small bodies into interstellar space. These objects would wander the galaxy indefinitely, occasionally passing near other stars. Oumuamua provided the first direct observational confirmation that this process is real and ongoing. Its trajectory showed that interstellar space is not dynamically empty. It contains debris shaped by planetary systems across the Milky Way, moving with velocities comparable to stars themselves. The solar system, rather than being isolated, is embedded in this broader population. Orbital mechanics did not merely identify Oumuamua's path. It established a new observational category. For the first time, astronomers could point to a specific object and say, with mathematical certainty, that it did not originate around our Sun. That conclusion was not based on appearance, composition, or speculation, but on gravity alone. And gravity, in this case, left no ambiguity. Once the orbit of Oumuamua was securely established as hyperbolic, attention turned to a different but equally important question. Not just where it was going, but where it came from. In celestial mechanics, direction and speed carry as much information as orbital shape. Together, they encode an object's dynamical history. The key quantity in this analysis was Oumuamua's incoming velocity before it encountered the Sun's gravitational field. This velocity is best interpreted in a reference frame tied not to Earth or even to the Sun alone, but to the average motion of stars in the Sun's local galactic neighbourhood. This frame is known as the local standard of rest, often abbreviated in lowercase as LSR. The LSR represents the mean motion of nearby stars orbiting the centre of the Milky Way. When velocities are measured relative to this frame, random stellar motions average out, revealing whether an object is moving unusually fast or slow compared to its surroundings. This is the natural frame in which to evaluate the origin of interstellar objects. When Oumuamua's velocity was transformed into the LSR frame, the result was striking. Its speed was modest, roughly 26 kilometers per second, which corresponds to about 16 miles per second. In galactic terms, this is not extreme. It is comparable to the typical velocity dispersion of stars in the solar neighbourhood. This immediately ruled out several scenarios. Objects ejected from the solar system by planetary encounters acquire their excess velocity through gravitational interactions, most commonly with Jupiter. These interactions tend to produce specific velocity signatures. Ejected bodies typically leave with velocities only slightly above the solar escape speed, resulting in velocities at infinity close to zero. Any significant excess speed would require an unusually energetic and finely tuned encounter. Oumuamua did not show such a signature. Its incoming velocity was not small. It was not barely unbound. It was already moving through interstellar space at a speed consistent with objects orbiting the galaxy, not with debris recently expelled from the Sun's gravitational influence. Equally important was the direction from which it arrived. Oumuamua approached the solar system from a region of the sky close to the solar apex, the direction toward which the Sun itself is moving relative to nearby stars. This is a subtle but crucial detail. If interstellar objects are part of a background population drifting through the galaxy, then in the Sun's frame they should preferentially appear to come from the direction the Sun is moving into, much like raindrops appearing to come from the direction a moving car is heading. This is exactly what was observed. The approach direction was not random, nor did it align with the plane of the planets or any known solar system structure. Instead, it was consistent with a background population of interstellar debris roughly at rest in the LSR, being overtaken by the Sun as it orbits the Milky Way. This behavior is difficult to reconcile with a solar system origin. If Oumuamua had been ejected from the solar system, its outgoing trajectory would be correlated with the geometry of planetary encounters, most likely involving Jupiter or Saturn. Such trajectories are not isotropic, nor are they aligned with the solar apex. They cluster along specific dynamical pathways shaped by planetary orbits. Oumuamua's path showed no such correlation. The phrase often used to describe its velocity is that it was too normal. This is not casual language. In dynamics, extremes are often easier to explain than averages. A very fast object might suggest an energetic interaction or a violent origin. A very slow object might suggest recent ejection. Oumuamua did neither. Its velocity was statistically unremarkable. This normality strongly supports the interpretation that Oumuamua was not a special case, but a random member of a much larger population. It behaved like an object that had been drifting through interstellar space for a long time, gradually thermalized into the velocity distribution of stars in the galactic disk. This conclusion carries significant statistical weight. If Oumuamua had been detected with an unusually high or low velocity, it might be interpreted as a rare or extreme event. Instead, its velocity suggests that interstellar objects are common enough and old enough to have their motions randomized by galactic dynamics. Over millions to billions of years, gravitational interactions with stars, molecular clouds, and the galactic potential itself erase the memory of an object's birthplace. Oumuamua appeared dynamically old. This has direct implications for the population of interstellar objects. Models of planet formation predict that young planetary systems eject vast numbers of small bodies during their early chaotic phases. These bodies are launched into interstellar space with a wide range of velocities, but over time their motions converge toward the velocity dispersion of stars. Oumuamua's kinematics fit this expectation remarkably well. From a statistical perspective, this means that its detection was not the result of an unusually energetic or nearby ejection event. Instead, it implies a steady-state background population of interstellar debris permeating the galaxy. The solar system simply happened to intersect one of these objects at the right time and geometry for detection. This realization also helps explain why Oumuamua was not detected earlier in its approach. Objects arriving from near the solar apex spend much of their inbound trajectory close to the sun's apparent position in the sky, making them difficult to observe with ground-based telescopes. This creates a strong observational bias against detecting such objects before perihelion. In other words, Oumuamua was not unusual for being detected late. Many interstellar objects may pass through the inner solar system unnoticed because of similar geometrical constraints. Statistical estimates based on a single detection are necessarily uncertain, but even conservative analyses suggest that objects of Oumuamua's size may pass through the inner solar system on timescales of years to decades. Smaller objects would be far more numerous, but largely invisible to current surveys. The velocity distribution strengthens this conclusion. If interstellar objects were rare, the probability of detecting one with such a typical velocity would be low. The fact that the first detected example already fits the expected background distribution suggests that the underlying population is large. This does not mean Oumuamua was typical in all respects. Its physical properties would later prove unusual, but dynamically it behaved exactly as a long-lived interstellar object should. The Sun, moving through the Milky Way at tens of kilometers per second, acts like a net sweeping through a diffuse cloud of debris. Occasionally, one of these objects passes close enough to be detected. When it does, its speed and direction tell a quiet but powerful story. Not of a dramatic ejection, not of a recent collision, but of a galaxy filled with planetary remnants, drifting for immense spans of time, largely invisible until a brief encounter brings one into view. In this sense, Oumuamua's speed and direction did more than trace its past. They revealed that the solar system is not isolated in a vacuum, but embedded in a dynamic galactic environment where material from other stars passes by with unremarkable regularity. The motion was ordinary, the implication was not. As soon as Oumuamua was confirmed as interstellar, attention shifted to its physical nature. With no spacecraft nearby and no resolved images available, astronomers had to rely on indirect methods. Among these, the most powerful tool was photometry, the precise measurement of how the object's brightness changed over time. The result was unlike anything previously observed for a small body in the solar system. Over multiple observing campaigns, Oumuamua exhibited dramatic brightness variations as it rotated. The observed light curve showed changes in brightness by a factor of about 10 between its minimum and maximum values. Expressed in astronomical magnitude units, this corresponds to a peak-to-trough variation of roughly 2.5 magnitudes. This immediately set Oumuamua apart. For comparison, most asteroids show brightness variations of less than a factor of 2 as they rotate. Even highly elongated asteroids typically produce light curve amplitudes corresponding to brightness ratios of 3 or 4. Comet nuclei, when inactive, tend to show similarly modest variations. A factor of 10 is extreme. Brightness variations in unresolved objects are driven primarily by changes in projected cross-sectional area as the object rotates. In simple terms, as an object spins, it presents different silhouettes to the observer. A nearly spherical body looks similar from all angles and produces little variation. An elongated body, by contrast, alternates between presenting its long side and its narrow end, leading to large brightness swings. Under the assumption that Oumuamua's surface reflectivity was relatively uniform, the observed light curve implies an extreme axis ratio, the ratio between its longest and shortest dimensions. Early estimates suggested a ratio of at least 5 to 1 and possibly as high as 10 to 1. This would make Oumuamua more elongated than any known asteroid observed to date. For context, even the most elongated contact binary asteroids rarely exceed ratios of about 3 to 1. However, axis ratio estimates depend on assumptions. One key assumption is shape. The simplest model is a prolate ellipsoid, essentially a stretched cigar shape. In this scenario, the observed brightness variations can be directly translated into a minimum elongation, but alternative geometries are possible, and some of them produce similar photometric signatures. This led to a fundamental debate about Oumuamua's true shape. One proposed model was a cigar-like object, long, thin, and rotating end over end. In this configuration, the large light curve amplitude arises naturally from the dramatic difference between the projected area when viewed side-on versus end-on. Such shapes are rare but not impossible, especially if formed through energetic processes like tidal disruption or collisional fragmentation. Another proposed model was nearly the opposite. A pancake-like shape, thin, flattened, and disc-like. In this case, brightness variations arise when the object alternates between face-on and edge-on orientations. A sufficiently thin disk can also produce large amplitude variations without requiring extreme length. Photometric data alone cannot uniquely distinguish between these two classes of shapes. However, additional constraints came from rotational dynamics. The light curve was not strictly periodic. Instead of repeating smoothly with a single rotation period, it showed complex, non-repeating patterns. This indicated that Oumuamua was not rotating about a single principal axis. It was tumbling, undergoing non-principal axis rotation. This matters for shape modelling. Highly elongated or flattened objects are more susceptible to tumbling, especially if they have experienced past collisions or tidal interactions. Tumbling also complicates light curve interpretation because the apparent rotation period can vary depending on orientation and viewing geometry. Nonetheless, even accounting for tumbling, the amplitude of the brightness variations remained too large to explain without invoking an extreme geometry. Surface reflectivity variations were also considered. In principle, a roughly spherical object with strong albedo contrasts, bright patches and dark regions, could mimic a large light curve amplitude. But this explanation was strongly disfavoured. To reproduce a factor of 10 brightness change through albedo alone would require implausibly sharp and stable reflectivity contrasts across the surface, with no accompanying spectral variations. Observations did not support this. The shape had to be extreme. Estimates of Oumuamua's absolute brightness, combined with assumptions about reflectivity, placed its characteristic size in the range of tens to a few hundred meters. If it were cigar-shaped, this would imply a length of perhaps 100 to 400 meters, with a width of only 10 to 40 meters. If disc-shaped, it might be tens of meters thick, but a few hundred meters across. Either way, the geometry was unprecedented. This raised a deeper physical question. How could such an object remain intact? Highly elongated or flattened bodies experience significant internal stresses as they rotate. Centrifugal forces act to pull material apart, especially at higher spin rates. For many asteroids, rotation periods shorter than about 2 hours lead to structural failure unless the object is monolithic rock with substantial tensile strength. Oumuamua's rotation period, inferred from its complex light curve, was on the order of several hours. This is slow enough to avoid immediate breakup, but still places constraints on its internal structure. If Oumuamua were a loosely bound rubble pile, a gravitational aggregate of smaller pieces, maintaining such an extreme shape would be difficult. Rubble piles tend to relax toward more compact configurations over time. Extreme elongation would be dynamically unstable unless the object had internal cohesion. This suggests that Oumuamua was either monolithic or possessed significant material strength. Several formation scenarios were proposed to explain such a shape. One involved tidal disruption during a close encounter with a star or massive planet in its original system. Such encounters can stretch bodies into elongated forms, especially if they occur near the tidal limit. Another possibility was collisional fragmentation, followed by selective survival of the most elongated fragments. A more speculative idea involved long-term erosion by interstellar dust. Over millions of years, preferential sputtering of surface material could gradually sculpt an initially irregular body into a more elongated or flattened shape. While such processes are slow, the timescales involved in interstellar travel are immense. Importantly, none of these scenarios require exotic physics. What they require is time. The interstellar environment is not violent, but it is persistent. Cosmic rays, micrometeoroid impacts, and thermal cycling act continuously. Over hundreds of millions or billions of years, even subtle effects can reshape small bodies in ways rarely seen within the relatively sheltered environment of a planetary system. Oumuamua's extreme geometry may therefore be less a mystery of origin than a record of exposure. The solar system has few objects that look like this, not because such shapes are impossible, but because solar system bodies are relatively young, dynamically active, and frequently reshaped by collisions and gravitational interactions. An object that has spent most of its existence drifting between stars may preserve configurations that are statistically rare in bound populations. By studying its light curve and inferred shape, astronomers were not simply measuring dimensions. They were probing mechanical strength, formation history, and long-term dynamical evolution. Oumuamua did not just arrive from another star system. It arrived carrying a geometry that solar system processes rarely produce, and even more rarely preserve. One of the most revealing aspects of Oumuamua was not its speed, or even its shape, but the way it rotated. Rotation state is a powerful diagnostic in small body physics. It preserves information about past interactions, internal structure, and the mechanical properties of an object over long time scales. In Oumuamua's case, the rotation did not behave as expected. Early photometric monitoring showed that its brightness variations did not repeat with a single stable period. Instead of a clean periodic light curve, astronomers observed irregular, quasi-periodic fluctuations. The peaks and troughs shifted subtly from one rotation cycle to the next. This immediately ruled out simple rotation around a single principal axis. the object was tumbling. In technical terms, Oumuamua was in a state of non-principal axis rotation. Rather than spinning smoothly like a balanced top, it rotated around multiple axes simultaneously. This kind of motion is well understood in rigid body dynamics and is common in objects that have experienced past disturbances. Non-principal axis rotation requires energy. In a purely rotating system, energy tends to dissipate toward the lowest energy configuration. Rotation around the axis with the largest moment of inertia. For an elongated object, this corresponds to rotation about its shortest axis. Any deviation from this state introduces internal stresses that gradually convert rotational energy into heat, damping the tumbling motion. The key question was not whether Oumuamua could tumble, but how it could still be tumbling. In the solar system, tumbling states are typically short-lived on astronomical timescales. For asteroids, collisions are the most common cause. A sufficiently energetic impact can knock an object into a complex rotational state. However, internal friction and structural dissipation usually damp this motion over timescales ranging from thousands to millions of years, depending on size, shape, and material properties. For Oumuamua, this raised an immediate issue. If it had been tumbling for a long time, then either the damping timescale had to be extremely long, or the tumbling had been excited relatively recently. Determining which of these scenarios applied required careful analysis of its physical properties and environment. One possibility was tidal interaction. When a small body passes close to a massive object, differential gravitational forces can torque it, altering its rotation state. This mechanism is well documented in cometary nuclei and near-Earth asteroids that experience close planetary flybys. In extreme cases, tides can even cause fragmentation. However, this explanation does not work for Oumuamua. Orbital reconstructions show no close encounter with any planet in the solar system prior to observation. Its perihelion distance, while inside Earth's orbit, was still far too large for solar tides to induce significant rotational excitation. Stellar tidal interactions in its original system were also considered unlikely, as such encounters would typically either disrupt the object entirely or leave other dynamical signatures. Tides were ruled out. This left two remaining broad categories: collisional excitation in the distant past, or intrinsic resistance to rotational damping. Collisions are common in young planetary systems, but extremely rare in interstellar space. Once an object is ejected into the galaxy, the density of potential impactors drops dramatically. The probability of a collision energetic enough to induce tumbling during interstellar travel is effectively negligible over billions of years. This strongly suggests that Oumuamua's tumbling state was either primordial, dating back to its ejection, or extremely long-lived. The timescale for damping non-principal axis rotation depends sensitively on internal structure. For a rigid, monolithic body made of solid rock or ice with significant tensile strength, energy dissipation can be very slow. In such cases, tumbling can persist for hundreds of millions or even billions of years. By contrast, for a porous or rubble pile object, an aggregate of loosely bound fragments, internal friction is much higher. Energy dissipates rapidly as components shift, collide, and deform. Tumbling in such objects damps out relatively quickly, often within less than 1,000,000 years. This distinction is critical. If Oumuamua were a rubble pile, its tumbling should have damped long before it ever reached the solar system. The fact that it was still tumbling strongly argues against a highly porous, loosely bound structure. Instead, the data favour a body with substantial rigidity. This interpretation is consistent with other constraints. Its extreme elongation or flattening would be mechanically unstable for a rubble pile. Maintaining such a shape over long timescales requires internal cohesion. The rotation period, while not fast enough to cause immediate breakup, would still impose stresses that a loosely bound aggregate would struggle to withstand. Models of rotational energy dissipation reinforce this picture. For a rigid body of Oumuamua's estimated size, on the order of tens to hundreds of meters, Damping timescales can exceed 1 billion years if internal friction is low. This places the tumbling state well within the expected lifetime of an interstellar object drifting through the galaxy. In this context, tumbling becomes a fossil record. It encodes information about the object's formation and early history, preserved because subsequent interactions were too weak to erase it. Oumuamua's tumbling likely originated during a violent phase in its parent planetary system, perhaps during ejection via close encounters with giant planets, or during a disruptive event that imparted both extreme shape and complex rotation. Importantly, tumbling also affects how other properties are interpreted. Non-principal axis rotation complicates light curve analysis, making it harder to infer precise shape and size. It also affects thermal modelling, because different surface regions experience changing illumination patterns. This has implications for surface temperatures, thermal stresses, and any potential outgassing processes. In later analyses, tumbling became a key input when evaluating non-gravitational accelerations and thermal forces acting on Oumuamua. Without accounting for its complex rotation, those models would be incomplete. What makes Oumuamua particularly instructive is that its rotation state bridges multiple domains of physics: rigid body dynamics, material science, and planetary formation. It is rare to encounter a natural object where these connections are so clearly exposed. The solar system contains tumbling objects, but most of them are dynamically young or recently disturbed. Oumuamua was neither. Its tumbling was not a transient state, but a long-lived condition carried across interstellar space. That fact alone provides a constraint that no spectrum or image could offer. It tells us that Oumuamua was mechanically strong, dynamically old, and shaped by processes that occurred long before it ever encountered the sun. With no resolved imagery and only a short observational window, nearly everything known about the surface of Oumuamua comes from its interaction with light. Colour indices, reflectance spectra, and brightness behaviour across wavelengths provided the only direct clues to its composition and surface history. These measurements were limited in precision by the object's faintness and rapid recession, but even so, they revealed a surface unlike most small bodies previously observed passing through the inner solar system. Optical observations were carried out using large ground-based telescopes shortly after discovery, including broadband photometry and visible filters and low-resolution spectroscopy extending into the near-infrared. Across these data sets, a consistent pattern emerged. Oumuamua exhibited a red spectral slope in the visible range, meaning its reflectance increased with wavelength from blue to red light. This property immediately placed it within a known class of solar system materials. Red spectral slopes are common among outer solar system objects, particularly Kuiper belt objects, and some inactive cometary nuclei. These surfaces are typically coated with complex, organic-rich materials formed through long-term irradiation of simpler ices. In contrast, inner solar system asteroids often display neutral or even bluish spectral slopes, reflecting rocky or metal-rich compositions that have undergone extensive thermal processing. Quantitatively, Oumuamua's visible spectral slope was measured to be comparable to moderately red Kuiper belt objects, but not among the reddest known surfaces. It did not exhibit the extreme redness seen in some dynamically cold Kuiper belt populations. Instead, it fell within the range associated with objects that have experienced partial resurfacing or thermal alteration. Near-infrared observations extended this picture. Within the limits of signal-to-noise, the spectrum appeared relatively featureless. No strong absorption bands attributable to water ice, hydrated minerals, or common silicates were detected. This absence of diagnostic spectral features constrained surface composition, but did not uniquely identify it. Featureless spectra are not uncommon. Many small bodies, particularly cometary nuclei that have lost their surface volatiles, exhibit low-contrast spectra dominated by dark carbon-rich materials. These materials absorb strongly across a wide range of wavelengths, suppressing identifiable absorption features. As a result, compositional interpretation relies more on overall slope and albedo than on discrete spectral lines. Albedo estimates for Oumuamua were uncertain due to the unknown shape and orientation of the object. However, reasonable assumptions based on its brightness and inferred size suggest a low albedo, likely in the range of a few percent to perhaps 10%. This places it among the darker small bodies in the solar system consistent with carbonaceous or organic-rich surfaces. Low albedo combined with red spectral slope is a familiar combination. It characterizes many dormant or extinct comets, objects that once exhibited volatile-driven activity but have since developed insulating surface layers that suppress outgassing. It also characterizes a large fraction of Kuiper Belt objects that have never approached the Sun closely enough to lose their surface volatiles, but have nonetheless undergone long-term space weathering. This raised an important question. If Oumuamua's surface resembled that of volatile-rich bodies, why did it show no cometary activity? As Oumuamua passed within approximately 0.25 astronomical units of the Sun, surface temperatures should have exceeded those required to sublimate water ice, carbon dioxide ice, and carbon monoxide ice if these materials were present near the surface. Yet deep imaging failed to detect any dust coma or tail, and spectroscopic searches found no evidence of gas emission. This absence of activity was one of the most puzzling aspects of the object. Several explanations were considered. One possibility was that Oumuamua was intrinsically volatile poor, more asteroid-like than comet-like despite its red surface. However, this would require a surface composition rich in organics but depleted in volatiles, a combination that is difficult to produce in known solar system environments without significant thermal processing. Another possibility was that volatile materials existed beneath the surface but were sealed off by an insulating mantle. This idea has strong precedent. Cometary nuclei that have made multiple passages near the Sun often develop refractory crusts composed of dust and organic residues. These layers can be only a few centimeters thick, yet they are sufficient to suppress sublimation by limiting heat transfer to underlying ice. In the case of Oumuamua, such a mantle could plausibly be much thicker. As an interstellar object, Oumuamua would have spent a vast amount of time exposed to cosmic rays, interstellar ultraviolet radiation, and micrometeoroid impacts. These processes chemically alter surface materials, breaking molecular bonds and driving polymerization reactions that produce complex carbon-rich residues. Over time, this leads to the formation of a radiation-processed layer that is both dark and thermally insulating. Laboratory experiments and modelling studies show that irradiation of icy mixtures can produce such mantles on timescales of tens to hundreds of millions of years. Given that Oumuamua was likely much older than this, the development of a thick devolatilised surface layer is not only plausible, but expected. This interpretation helps reconcile several observations simultaneously: the red spectral slope, low albedo, lack of spectral features, and absence of detectable outgassing. Comparisons with Kuiper Belt objects further support this view. Many KBOS display red colours attributed to radiation-processed organics, yet they show no activity because they reside at large heliocentric distances where sublimation is negligible. When such objects are scattered inward and become centaurs, some exhibit delayed or weak activity, often requiring substantial heating before volatiles can break through surface layers. Dormant comets represent an even closer analogue. These objects occupy comet-like orbits but appear asteroid-like in terms of activity. Their surfaces are thought to be mantled with volatiles trapped beneath layers that may only become active after structural disruption or prolonged heating. Oumuamua behaved like an extreme version of this class. However, there were differences. Even dormant comets in the solar system often display at least weak dust emission near perihelion. Oumuamua did not. Upper limits on dust production were stringent, implying either an unusually effective insulating layer or a volatile inventory significantly different from that of typical solar system comets. The lack of detectable gas emission also placed constraints on surface chemistry. For example, carbon monoxide and carbon dioxide are far more volatile than water ice and can drive activity at much larger distances from the Sun. The absence of these gases suggests that if they were present, they were either deeply buried or had been depleted long before Oumuamua's arrival. This points again to long-term exposure in interstellar space. Cosmic ray irradiation plays a critical role here. High-energy particles penetrate tens of centimeters into icy materials, breaking apart volatile molecules and allowing lighter species to escape over time. This process selectively removes the most volatile components, leaving behind heavier, less volatile compounds and complex organics. Over millions to billions of years, this leads to a surface that is chemically altered, devolatilized, and mechanically robust. Such a surface would be dark, red, spectrally featureless, and resistant to sublimation, precisely what was observed. Importantly, this does not require that Oumuamua formed without volatiles. It only requires that it lost or sequestered them during its long interstellar journey. The surface properties therefore encode both composition and history. They suggest formation in a cold, volatile-rich environment, followed by prolonged isolation and irradiation. This sequence is consistent with formation in the outer regions of a planetary system, subsequent ejection, and long residence in interstellar space. One must also consider observational limitations. Because Oumuamua was faint and rapidly fading, spectroscopic data were limited in wavelength coverage and signal quality. Subtle absorption features may have been present but undetectable. The absence of evidence is not evidence of absence. However, the consistency across independent datasets strengthens confidence in the broad conclusions. Taken together, the surface observations place Oumuamua closer to outer solar system bodies than to inner solar system asteroids, despite its lack of activity. It occupied an intermediate category, compositionally comet-like, behaviorally inert. This combination is not contradictory when viewed through the lens of surface evolution. The surface of Oumuamua was not pristine. It was the product of extreme duration rather than extreme temperature. Its colour and reflectance were shaped not by repeated solar heating, but by cosmic radiation accumulated over immense spans of time. In this sense, its surface did not just reflect light, it recorded exposure. And through that record, astronomers gained a rare opportunity to study material that had evolved outside the solar system under conditions rarely accessible to direct observation. Once the trajectory of Oumuamua had been reconstructed with high precision, astronomers noticed something unexpected. Even after accounting for the gravitational influence of the Sun and planets, the object's motion did not follow a purely Keplerian path. The deviation was small, but it was systematic, reproducible, and statistically significant. This marked the beginning of one of the most intensively analysed aspects of Oumuamua's behaviour, its non-gravitational acceleration. Astrometric measurements are the foundation of orbit determination. Each data point records the object's position against background stars with sub-arc-second precision. For Oumuamua, hundreds of such measurements were collected over several weeks using large telescopes. When these positions were fit using a purely gravitational model, residuals remained. These residuals were not random. They showed a consistent pattern indicating an additional acceleration acting on the object. The magnitude of this acceleration was small, on the order of 10 to the minus 6 meters per second squared near perihelion, but it was clearly above the noise level. More importantly, the acceleration was directed approximately radially away from the Sun and decreased with distance in a manner broadly consistent with a solar-driven process. In the solar system, non-gravitational accelerations are not unusual. They are commonly observed in comets and are typically caused by outgassing. As volatile ices sublimate, the escaping gas acts like a weak rocket engine, producing a recoil force that alters the object's trajectory. Naturally, this was the first explanation considered. However, when astronomers attempted to model Oumuamua's acceleration using standard cometary outgassing prescriptions, they encountered immediate problems. Classical comet models assume that water ice sublimation dominates near the Sun, producing both gas and dust. This activity generates a visible coma and often a tail which can be directly observed. Oumuamua showed none of this. Deep imaging placed stringent upper limits on dust production. Spectroscopic searches failed to detect gas species typically associated with cometary activity, including water vapor, carbon monoxide, and carbon dioxide. If outgassing were responsible for the observed acceleration, it would have had to occur without producing detectable byproducts. This is not impossible in principle, but it is highly constrained. The amount of force required to explain the acceleration corresponds to a significant mass loss rate if driven by typical cometary volatiles. Such mass loss would almost certainly produce observable signatures unless the outgassing were composed of an unusual, dust-free species or occurred in a highly collimated and transient manner. Moreover, classical outgassing produces torques as well as forces. These torques tend to alter an object's rotation state, often measurably so. In the case of Oumuamua, no significant change in rotation rate or tumbling behavior was observed over the period during which the non-gravitational acceleration acted. This absence of rotational evolution posed an additional challenge for standard outgassing models. Given these difficulties, alternative mechanisms were explored. One such mechanism was solar radiation pressure. Photons carry momentum, and when they strike an object, they exert a force. For most asteroids and comets, this force is negligible compared to gravity. However, if an object has an unusually large surface area to mass ratio, radiation pressure can become dynamically significant. This idea attracted attention because radiation pressure naturally produces an acceleration directed away from the Sun and declines with the inverse square of distance, matching the observed trend qualitatively. Quantitatively, however, the requirements were severe. To generate the observed acceleration through radiation pressure alone, Oumuamua would need to have an extremely low mass per unit area. This implies either an object that is extraordinarily thin or one with a very low bulk density, or both. Simple calculations showed that a solid rocky body of typical asteroid density could not experience such acceleration from sunlight. Models invoking radiation pressure therefore required Oumuamua to be either a thin sheet-like structure or a highly porous, low-density body. These models were not ruled out by astrometry alone, but they introduced tensions with other observations. A highly porous object would likely dissipate rotational energy rapidly and would struggle to maintain the extreme shape inferred from light curve analysis. A very thin structure would face challenges related to mechanical stability and survivability over interstellar travel times. Additionally, radiation pressure would act uniformly across the object's illuminated surface. This uniformity would not naturally explain the lack of torque unless the object's shape and orientation were finely tuned. While not impossible, this added further constraints. Another category of models focused on non-standard outgassing. Instead of water vapor, researchers considered the sublimation of more volatile or less observable species. Molecular hydrogen, for example, produces no strong spectral signatures at optical or near-infrared wavelengths. Nitrogen ice was also proposed, inspired by the surface composition of Pluto and other icy bodies. In these scenarios, sublimation could generate sufficient thrust without producing dust or detectable gas emission. However, these models faced their own difficulties. Hydrogen ice is extremely volatile and would not survive long in interstellar space unless shielded by an insulating layer. Nitrogen ice, while more stable, would still require specific formation conditions and would need to survive both interstellar exposure and solar heating without fragmenting. Thermal modelling showed that sustaining the required mass loss over the observed time interval without violating other constraints was challenging. While some exotic outgassing models remained marginally viable, none provided a completely satisfactory explanation without invoking finely tuned assumptions. Throughout this process, statistical rigor was essential. The non-gravitational acceleration was detected at high significance, well above the level expected from astrometric noise or systematic errors. Independent analyses using different datasets and fitting techniques consistently recovered the same acceleration term. This eliminated the possibility that the effect was an artifact of data reduction or observational bias. At the same time, the uncertainty in the acceleration's exact functional form limited what could be inferred. The observational arc was relatively short, and Oumuamua was already receding when most data were collected. This meant that models could constrain the presence of an additional force, but not uniquely identify its physical origin. In practical terms, the data allowed astronomers to say with confidence that the motion deviated from pure gravity, but not to determine with certainty why. This distinction is critical. In scientific analysis, detecting an effect is separate from explaining it. For Oumuamua, the detection of non-gravitational acceleration is robust. The explanation remains open, bounded by observational limits and physical plausibility. What can be said is that any viable model must satisfy several constraints simultaneously. It must reproduce the magnitude and direction of the acceleration. It must avoid producing detectable dust or gas. It must not significantly alter the object's rotation state. It must be consistent with the inferred shape, size, and surface properties, and it must be physically stable over interstellar timescales. Few models meet all of these criteria comfortably. This has led to ongoing debate, not because the data are ambiguous, but because the phenomenon sits at the intersection of multiple physical regimes: celestial mechanics, thermodynamics, material science, and observational astronomy. Each regime imposes constraints that narrow the space of plausible explanations. Importantly, the existence of unexplained non-gravitational acceleration does not imply exotic technology or artificial origin. In planetary science, unexplained forces often point to incomplete understanding of natural processes under unfamiliar conditions. Oumuamua represented a class of object never before observed, and it would be surprising if existing models applied perfectly without modification. The broader implication is methodological. Oumuamua demonstrated that interstellar objects can behave differently from solar system bodies in subtle but measurable ways. Their surfaces, compositions, and histories may lie outside the parameter space on which comet and asteroid models are based. When such an object enters the solar system, it tests those models in regimes they were not designed to handle. The non-gravitational acceleration was therefore not just an anomaly, it was a signal that the physics of small bodies ejected from other planetary systems, processed for immense spans of time in interstellar space, may differ in important ways from the physics inferred from solar system examples alone. In this sense, the precise astrometric deviations observed in Oumuamua did more than complicate its trajectory. They expanded the scope of small body dynamics, forcing astronomers to confront the limits of their assumptions and to develop new frameworks for interpreting motion beyond gravity. The object left the solar system still accelerating slightly faster than gravity alone would predict. And that residual motion remains one of the clearest indicators that Oumuamua was not just passing through space, but revealing gaps in our understanding as it did so. With classical cometary activity unable to explain the non-gravitational acceleration of Oumuamua, attention shifted toward less conventional, but still entirely natural, outgassing mechanisms. These models aimed to reproduce the observed acceleration while remaining consistent with the absence of detectable dust, the lack of standard gas emissions, the object's rotation state, and its inferred surface properties. The constraints were narrow and quantitative. Any viable mechanism had to generate an outward acceleration of order 10 to the minus 6 meters per second squared near perihelion, decrease with increasing distance from the Sun, avoid producing a visible coma, avoid altering the rotation state measurably, and remain physically stable over the long interstellar timescales implied by the object's galactic kinematics. One of the most widely discussed possibilities involved molecular hydrogen. Hydrogen has several properties that make it attractive in principle. It is extremely volatile, produces no dust, and has very weak spectral signatures in the optical and near-infrared. If hydrogen gas were released from beneath the surface, it could generate thrust without leaving easily detectable observational traces. Thermodynamically, hydrogen sublimates at very low temperatures. Even modest solar heating at distances beyond 1 astronomical unit would be sufficient to drive significant mass loss if hydrogen ice were present near the surface. Simple momentum balance calculations showed that a relatively small hydrogen mass loss rate could, in principle, account for the observed acceleration without violating observational upper limits on dust or common gas species. However, survivability emerged as the dominant problem. Hydrogen ice is extremely fragile in astrophysical environments. In interstellar space, it is exposed continuously to cosmic rays, ultraviolet photons, and the diffuse interstellar radiation field. These processes deposit energy that disrupts molecular hydrogen ice efficiently. Even when embedded within other materials, hydrogen diffuses readily through solids and escapes. Thermal and diffusion modeling indicates that a hydrogen-rich body of Oumuamua's inferred size would lose its hydrogen inventory on timescales far shorter than the millions to billions of years suggested by its velocity relative to the local standard of rest. Retaining enough hydrogen to drive outgassing near the Sun would require either an unrealistically thick insulating layer or formation in an environment where hydrogen ice could be both abundant and protected over extreme durations. Both conditions are difficult to reconcile with known astrophysical settings. Additionally, hydrogen outgassing would be expected to produce detectable cooling effects and potentially measurable torques. No significant rotational evolution was observed during the period when the acceleration was acting. While this does not formally exclude hydrogen, it places the model under severe tension. A second proposal involved nitrogen ice. Nitrogen ice is well documented in the solar system, most notably on Pluto and Triton, where it dominates surface composition. Nitrogen sublimates at higher temperatures than hydrogen, making it more resistant to long-term loss in interstellar space while still volatile enough to sublimate near the Sun. In this scenario, Oumuamua is interpreted as a fragment of a nitrogen-rich, icy body ejected from the outer regions of a planetary system during a violent event, such as a collision or tidal disruption. Long-term cosmic ray irradiation would darken and chemically process the surface, producing the observed red spectral slope and low albedo. Thermal models show that nitrogen sublimation near perihelion could generate sufficient thrust to explain the observed acceleration while producing little or no dust. Molecular nitrogen is spectroscopically difficult to detect in the optical and near-infrared, consistent with the lack of detected gas emission. This mechanism also avoids some of the torque problems associated with dust-laden outflows. However, this model introduces its own constraints. It requires nitrogen-dominated icy bodies to be common in other planetary systems. In the solar system, such bodies appear to be rare and confined to specific environments. Extending this composition to a substantial interstellar population implies formation conditions that may not be universal. Additionally, nitrogen ice sublimation is energetically efficient. Modelling indicates that substantial mass loss would occur during a close solar passage. This implies that the object's original size must have been larger than inferred from brightness alone, with significant erosion occurring even during a single perihelion passage. While not impossible, this requirement narrows the parameter space considerably. Survivability in interstellar space remains an issue as well. Nitrogen ice is more resistant to cosmic ray destruction than hydrogen, but still vulnerable over very long timescales unless protected by a thick crust. Such a crust would, in turn, suppress sublimation and reduce thrust, again tightening constraints. Carbon monoxide and carbon dioxide were also examined as possible drivers of non-gravitational acceleration. Both species are known to power activity in distant comets, sometimes well beyond the orbit of Jupiter. Carbon monoxide sublimates at very low temperatures and carbon dioxide at intermediate temperatures, making both physically plausible candidates. Thermal modelling showed that either species could, in principle, generate the required acceleration if present in sufficient quantities. However, both gases produce strong and characteristic spectral signatures. Carbon monoxide has prominent infrared and radio emission lines, while carbon dioxide produces distinctive infrared features. Observations placed strong upper limits on both species. While extremely low production rates cannot be excluded absolutely, the mass loss rates required to explain the acceleration would almost certainly have been detectable, particularly for carbon monoxide. In addition, CO and CO2-driven activity typically entrains dust, producing at least a weak coma. No such coma was observed, even at sensitivity levels well below those of weakly active comets. These constraints effectively rule out carbon monoxide or carbon dioxide as the dominant contributors to the observed acceleration. Across all proposed exotic outgassing models, thermal modelling reveals a fundamental tension. Volatiles that sublimate efficiently enough to drive acceleration tend to be fragile under cosmic radiation and difficult to preserve over interstellar timescales. Volatiles that survive long-term irradiation tend to be too refractory to sublimate rapidly without producing detectable byproducts. This tension is not a failure of physics, but a reflection of boundary conditions rarely encountered in solar system studies. Oumuamua experienced thermal conditions, radiation exposure, and evolutionary histories that differ substantially from those of typical comets and asteroids bound to the Sun. The tumbling rotation further complicates thermal behavior. Non-principal axis rotation distributes solar heating irregularly across the surface, affecting sublimation efficiency and temporal response. Any successful model must reproduce not only the magnitude of the acceleration, but also its smooth evolution without inducing rotational instability. Importantly, none of the exotic outgassing models require new physics. They rely on known materials and well-understood thermodynamic processes. Their difficulty lies in simultaneously satisfying all observational constraints rather than in violating physical law. From a broader perspective, the inability to identify a single, clean explanation may itself be informative. Planetary systems vary widely in composition and formation pathways. Interstellar objects represent a statistical sampling of that diversity. It is therefore plausible that Oumuamua belongs to a class of objects whose dominant volatile inventory and surface evolution are uncommon or absent in the solar system. In this context, exotic outgassing may not be exotic in the galaxy at large, but only unfamiliar to observers accustomed to solar system bodies. What Oumuamua provided was not a definitive mechanism, but a sharply bounded parameter space. Any explanation must operate within those bounds, constrained by astrometry, spectroscopy, thermal physics, and long-term survivability. And within those constraints, the object continues to serve as a reminder that interstellar small bodies may obey the same physical laws as solar system objects, while occupying regions of parameter space that solar system science has only just begun to explore. Understanding the origin of Oumuamua requires stepping far beyond the solar system and into the environments where planetary systems form. The key question is not how such an object behaved once it entered interstellar space, but how it was launched there in the first place. This is a problem of planet formation, disk dynamics, and gravitational scattering on large scales. Planetary systems form within protoplanetary disks, rotating disks of gas and dust surrounding young stars. These disks are dense, turbulent, and dynamically active. Within them, solid particles collide, grow, fragment, and migrate. At the same time, giant planets form and begin to reshape the disk through their gravity. From a dynamical standpoint, these environments are extremely efficient at ejecting material. Simulations of protoplanetary disks consistently show that a large fraction of solid material does not end up in planets. Instead, it is scattered, redistributed, or expelled entirely. The most effective agents of ejection are massive planets, particularly gas giants. Once a giant planet forms, its gravitational influence extends far beyond its immediate orbit, perturbing smaller bodies and placing them onto unstable trajectories. Gravitational scattering operates through repeated close encounters. A small body passing near a massive planet can exchange energy and angular momentum. Over multiple encounters, this process can gradually increase the object's orbital eccentricity until it exceeds unity, at which point the object is no longer bound to the star and escapes into interstellar space. This mechanism is well documented in the solar system. Jupiter, for example, is known to eject comets from the outer solar system efficiently. Dynamical models indicate that Jupiter has expelled far more material than it has retained over the age of the solar system. The same process is expected to operate in other planetary systems, particularly those with multiple giant planets or planets undergoing migration. Planetary migration plays a crucial role here. During the early stages of disk evolution, giant planets are not stationary. Interactions with the gas disk can cause them to migrate inward or outward over relatively short timescales, sometimes moving several astronomical units in less than 1 million years. As they migrate, they sweep through populations of smaller bodies, destabilizing entire regions of the disk. This process dramatically enhances ejection efficiency. When a giant planet migrates, it does not simply scatter objects locally. It reshapes resonances, destabilizes previously stable orbits, and injects energy into the surrounding population. Numerical simulations show that migrating giant planets can eject tens of Earth masses of solid material into interstellar space. Importantly, this material is not compositionally uniform. Objects ejected from different regions of the disk carry signatures of their formation environment. Bodies formed closer to the star tend to be rocky and volatile poor, while those formed farther out incorporate increasing amounts of ices. The precise composition depends on the disk's temperature structure, chemical gradients, and evolutionary history. In this context, Oumuamua's inferred properties are informative. Its surface characteristics suggest formation in a cold environment, likely beyond the ice lines of its parent system. At the same time, its lack of classical cometary activity implies substantial surface processing, consistent with long-term exposure after ejection. Simulations of planet formation consistently predict that the majority of ejected material originates from the outer regions of planetary systems. These regions contain the largest reservoirs of solid mass and are most strongly perturbed by giant planets. As a result, interstellar space should be populated primarily by icy or ice-rich bodies, many of which will later evolve into inactive or dormant states. The predicted number of such objects is large. Population synthesis models that combine planet formation, migration, and scattering processes estimate that each planetary system can eject on the order of 1 to 10 Earth masses of solid material over its lifetime. When averaged over the billions of stars in the Milky Way, this implies an enormous population of interstellar debris. Translating this into number density depends on assumptions about size distributions. If the ejected mass is dominated by objects tens to hundreds of meters in size, then the number density of interstellar objects could be high enough to explain the detection of Oumuamua after only a few years of systematic sky surveys. Several independent studies have reached this conclusion. When realistic size distributions are assumed, the inferred detection rate of interstellar objects becomes consistent with Oumuamua being the first observed example rather than an extreme outlier. In fact, some models suggest that objects of similar size may pass through the inner solar system every few years, with smaller ones doing so far more frequently. The key limiting factor is detection sensitivity, not abundance. This has important implications for how representative Oumuamua may be. If interstellar objects are common, then the first detected example is likely to reflect typical formation and ejection processes rather than rare or exotic events. Its unusual properties would then arise not from exceptional origins, but from long-term evolution in interstellar space combined with observational bias. The role of stellar environment must also be considered. Stars do not form in isolation. Most are born in clusters, where close stellar encounters are far more frequent than in the present-day galactic field. In such environments, gravitational interactions between stars can truncate disks, perturb planetary systems, and directly eject material. This process can operate even before giant planets fully form. Cluster dynamics therefore provide an additional pathway for ejecting material into interstellar space. Objects launched in this way may carry different dynamical and compositional signatures compared to those ejected by planets alone. Over time, however, these differences are erased by galactic mixing. From this perspective, Oumuamua does not point to a single formation pathway. Instead, it represents the integrated outcome of many possible processes operating across diverse planetary systems. What it does suggest is that the solar system is not unique in its efficiency at ejecting material. If anything, systems with multiple giant planets or strong migration histories may be even more efficient. Observations of exoplanetary systems reveal that such architectures are common. Hot Jupiters, eccentric giants, resonant chains, and compact multi-planet systems all imply a history of dynamical instability and migration. These conditions are precisely those that favour strong scattering and mass loss. In that sense, Oumuamua may be a typical product of typical planetary systems. Its existence supports the idea that planet formation is a violent and inefficient process, producing vast amounts of debris that never becomes part of a stable planet. Instead, this material is expelled, contributing to a galaxy-wide population of small bodies that wander between stars. This reframes how planetary systems are understood. Rather than being closed systems that retain most of their solid material, they appear to be open systems that exchange mass with the interstellar medium. Over cosmic time, this exchange becomes significant. Material processed in one system can pass through another, potentially delivering chemically altered solids across stellar boundaries. While Oumuamua itself did not interact strongly with the solar system, its mere passage demonstrates that such exchanges occur. The object did not require an unusual origin, a rare star, or an exotic formation environment. It required only what planet formation models already predict: massive disks, migrating planets, and gravitational scattering operating over long time scales. What made Oumuamua notable was not where it came from, but that it was finally observed. In that sense, it serves as an empirical anchor for decades of theoretical work. It confirms that interstellar debris is not just a theoretical expectation, but a measurable component of the galaxy. And by doing so, it provides indirect evidence about planetary systems we cannot observe directly, that they form planets inefficiently, eject material copiously, and populate interstellar space with the remnants of their formation histories. The discovery of 2E Borisov in August 2019 provided the first opportunity to compare two interstellar objects directly. Unlike Oumuamua, which was detected only after perihelion and displayed no obvious cometary activity, 2I Borisov. 2I Borisov behaved in a way that would have appeared entirely ordinary had it been a native member of the solar system. This contrast is central to understanding what interstellar objects can be and what their diversity implies about planetary systems beyond the Sun. From the moment of its discovery, 2I Borisov exhibited a clear coma and dust tail. Imaging revealed an extended cloud of gas and dust surrounding a compact nucleus, with morphology and brightness evolution consistent with an actively outgassing comet. Spectroscopic observations quickly confirmed the presence of volatile species commonly seen in solar system comets, including cyanogen and diatomic carbon. Later observations detected carbon monoxide at unusually high abundance. This immediately distinguished Borisov from Oumuamua. The non-gravitational acceleration observed in Borisov's orbit could be explained entirely by classical cometary outgassing. When standard models of gas-driven recoil were applied, the astrometric residuals vanished without requiring exotic assumptions. The magnitude, direction, and temporal evolution of the acceleration were all consistent with mass loss driven by sublimation of volatile ices as the comet approached the Sun. In other words, Borisov behaved exactly as expected. Its dust production rate, gas emission ratios, and coma morphology fell within the known range of long-period comets originating from the solar system's Oort cloud, while some compositional differences were noted, particularly its high carbon monoxide content relative to water. These differences were quantitative rather than qualitative. Borisov was not outside the known parameter space of cometary behavior. This raised an immediate question. Why did the first detected interstellar object look so different from the second? The most straightforward answer is compositional diversity. Planetary systems form under a wide range of conditions. Disk temperatures, chemical abundances, radiation environments, and formation timescales vary from star to star. As a result, the small bodies produced and later ejected by these systems need not resemble one another closely. In this context, it would be surprising if all interstellar objects behaved like comets, or like asteroids, or like any single solar system population. Oumuamua and Borisov may simply occupy different ends of a broad distribution. Borisov was gas-rich. Its nucleus contained substantial amounts of volatile ices near the surface, readily accessible to solar heating. When it entered the inner solar system, these ices sublimated efficiently, driving activity and producing a classic cometary appearance. Oumuamua, by contrast, appeared volatile poor at the surface. Whether due to intrinsic composition or long-term processing, its near-surface layers did not respond to solar heating with detectable gas or dust release. If volatiles were present, they were either deeply buried, depleted, or composed of species that were difficult to detect. This distinction aligns naturally with expectations from formation and evolutionary history. Objects ejected early from their parent systems or from cold outer regions with limited processing are more likely to retain volatile rich surfaces. Objects ejected later or subjected to prolonged irradiation in interstellar space are more likely to develop devolatilized inert crusts. Over millions or billions of years, cosmic rays and ultraviolet radiation selectively remove or chemically transform the most volatile components. Borisov's surface appears to have retained a substantial fraction of its original volatile inventory. Oumuamua's surface did not. The size difference between the two objects may also play a role. Estimates suggest that Borisov's nucleus was several hundred meters across, possibly larger than Oumuamua's characteristic dimensions. Larger bodies can retain volatiles more effectively because their interiors are better shielded from radiation and thermal diffusion. Smaller bodies lose volatiles more rapidly and develop insulating mantles more efficiently. This size dependence introduces an important observational bias. Gas-rich objects like Borisov are far easier to detect. Their comae increase their effective cross-sectional area dramatically, making them visible at greater distances and for longer periods. Activity also provides clear diagnostic signatures that immediately identify them as comets. Inactive or weakly active objects like Oumuamua are much harder to find. They rely entirely on reflected sunlight from a small, solid body, and their detectability drops rapidly with distance. They are often discovered only after perihelion, when they move into darker skies and are already fading. As a result, detection statistics are skewed. The fact that the second detected interstellar object was a normal comet does not imply that most interstellar objects are comet-like. It implies that comet-like interstellar objects are easier to detect. The first detection may have been unusual precisely because it was not gas-rich, yet happened to pass close enough and with favourable geometry to be noticed. When these biases are taken into account, the contrast between Oumuamua and Borisov becomes less surprising. From a population perspective, the two objects suggest at least two broad classes of interstellar small bodies: those that remain volatile-rich and behave like comets, and those that are volatile-poor or surface-inert and behave more like asteroids or dormant comets. The relative proportions of these classes remain uncertain, but current detection methods favour the former. There are also subtler differences worth noting. Borisov's chemical composition showed signs of formation in a cold environment, but with abundances that differed from typical solar system comets. In particular, its carbon monoxide content was high relative to water, suggesting formation at very low temperatures or in a disk with different chemical pathways. This reinforces the idea that even among comet-like interstellar objects, diversity is expected. Oumuamua's surface spectrum, by contrast, lacked clear compositional signatures, but its red colour and low albedo pointed toward organic-rich materials similar to those found on outer solar system bodies. The absence of activity does not imply a rocky, asteroid-like origin in the inner regions of a planetary system. It may instead reflect extreme surface processing rather than intrinsic dryness. Taken together, the two objects argue against any single typical interstellar body. Instead, they support a picture in which interstellar space contains a mixture of fragments ejected from different regions of planetary systems at different times and with different subsequent evolutionary histories. Some retain volatile-rich surfaces and announce themselves as comets, others do not and remain observationally subtle. This diversity has important implications for models of planet formation and evolution. If planetary systems eject large amounts of material, as simulations predict, then the composition of that material should reflect the radial structure of the disk. Inner regions contribute rocky debris. Outer regions contribute icy bodies. Migration and scattering mix these populations before ejection. Interstellar space therefore becomes a repository of mixed planetary debris, sampling conditions across many systems. Borisov likely represents material ejected relatively early or from a cold, volatile, rich zone. Oumuamua may represent material that either formed in a similar zone but was ejected much earlier and processed for longer, or formed under different conditions altogether. Observational bias complicates attempts to infer population statistics from such a small sample. With only 2 confirmed detections, it is impossible to draw firm conclusions about relative abundances. However, the stark difference between these two objects already demonstrates that interstellar small body populations cannot be treated as homogeneous. Future surveys are expected to detect many more such objects. As sensitivity improves and sky coverage expands, especially with next-generation observatories, the detection of inactive or weakly active interstellar bodies should become more common. This will help balance the current bias toward gas-rich objects and provide a clearer picture of the true population distribution. In that future dataset, Oumuamua and Borisov will likely be seen not as anomalies, but as early representatives of a broad spectrum. One revealed that interstellar objects can be inert, elongated, and dynamically unusual. The other confirmed that some are indistinguishable from familiar comets, despite originating beyond the solar system. Together, they demonstrate that interstellar objects do not form a single class. They are the byproducts of diverse planetary systems, shaped by formation environments, ejection histories, and long-term evolution in interstellar space. And as observational capabilities improve, that diversity is likely to become one of the most informative aspects of this new field of study. The fact that Oumuamua was detected only after it had passed its closest approach to the Sun is not incidental. It is a direct consequence of how astronomical surveys work, where they look what they can see and what they systematically miss. Understanding this requires examining the geometry of detection, instrumental sensitivity, and the statistical limits imposed by current observing strategies. Modern sky surveys are optimized for detecting objects against a dark sky background. Ground-based optical telescopes cannot observe close to the sun because scattered sunlight in Earth's atmosphere overwhelms faint sources. As a result, regions within roughly 40 to 60 degrees of the sun are effectively blind to most asteroid and comet surveys. Objects approaching from these directions remain undetectable until they move into darker night skies. Oumuamua approached the inner solar system from a direction close to the solar apex, which lies near the sun's apparent position in the sky. For much of its inbound trajectory, it was hidden in daylight glare. It passed perihelion at a distance of about 0.25 astronomical units without being observed. Only after it had swung around the sun and moved outward, increasing its angular separation from the sun, did it enter the surveyable sky. This geometry alone explains the late detection. There was no failure of monitoring. The object was simply invisible to existing surveys until it was already receding. This is a fundamental limitation of Earth-based optical astronomy and applies equally to near-Earth asteroids, long-period comets, and interstellar objects. Brightness evolution further compounded the problem. Small bodies are brightest near perihelion when they are both closest to the sun and often closest to Earth. By the time Oumuamua became observable, it was already fading rapidly. Its peak brightness had passed, shortening the window during which it could be detected at all. Detection sensitivity is the next limiting factor. Surveys such as pan-stars are designed to cover large areas of sky quickly, trading depth for breadth. Their limiting magnitudes are typically around 22 to 23 in standard filters under good conditions. This is sufficient to detect kilometre-scale asteroids at large distances and tens-of-metre-scale objects only when they pass relatively close to Earth. Oumuamua was small, likely tens to hundreds of metres in characteristic dimension, and had a low albedo. Such objects are intrinsically faint. Even at its brightest, Oumuamua was near the detection threshold. Had it passed just slightly farther from Earth, or had its surface been marginally darker, it may not have been detected at all. This highlights an important bias. Current surveys are far more sensitive to large, bright, or active objects than to small, inert ones. Comets with comae can be detected at much greater distances because their dust and gas dramatically increase their effective brightness. Inactive interstellar objects rely entirely on reflected sunlight from a compact solid surface, making them much harder to detect. This bias explains why 2I Borisov was detected earlier in its approach and at greater distance than Oumuamua. Borisov's activity made it visible to surveys long before it entered the inner solar system. Oumuamua had no such advantage. Because of these biases, any estimate of interstellar object abundance must account for what surveys cannot see. Early statistical analyses attempted to infer population densities from the single detection of Oumuamua. While such estimates carry large uncertainties, they converge on a striking conclusion. To detect one object of Oumuamua's size within a few years of survey operation, the underlying population must be large. Simple volume-based arguments illustrate this. The effective detection volume for an inert object of Oumuamua's size is small, limited to a region where it is both bright enough and sufficiently separated from the sun in the sky. If one such object passed through that small volume during the survey lifetime, then many more must have passed through larger volumes unnoticed. Depending on assumptions about size distribution and velocity, estimates suggest that objects comparable to Oumuamua may pass through the inner solar system on timescales of years to decades. Smaller objects would be far more numerous, but almost entirely undetectable with current instruments. Larger objects would be rarer but easier to find. These estimates are consistent with theoretical predictions from planet formation models, which suggest that each planetary system ejects vast quantities of material into interstellar space. When averaged over the stellar density of the Milky Way, this produces a diffuse but non-negligible flux of interstellar debris through any given stellar system. Importantly, these objects do not cluster near the ecliptic plane. Unlike asteroids and comets native to the solar system, interstellar objects arrive from all directions. This isotropic arrival pattern further reduces detection efficiency because surveys often prioritize the ecliptic where solar system bodies are concentrated. Survey cadence also matters. Most wide-field surveys revisit the same region of sky on timescales of days. Fast-moving objects can cross large angular distances between observations, complicating orbit linking and increasing the chance that detections will be discarded as unassociated transients. This is especially problematic for interstellar objects, which have higher apparent velocities than typical asteroids. Oumuamua was successfully linked across multiple nights, but this required careful analysis and favourable circumstances. Many similar objects may be detected only once or twice and never recognized as real moving bodies. All of these factors mean that current surveys operate far from the theoretical limit of interstellar object detection. They are capable of finding only the most favorable cases, objects that are relatively large, pass close to Earth, arrive from observable directions, and are detected during a narrow temporal window. This is where future facilities become critical. The Vera C. Rubin Observatory represents a major shift in survey capability. Its legacy survey of space and time will combine wide sky coverage with unprecedented depth and cadence. Rubin will repeatedly image the entire visible sky every few nights, reaching limiting magnitudes around 24.5 in single exposures and even deeper when images are combined. This increase in depth translates directly into detection volume. An inert object like Oumuamua could be detected at significantly greater distances, extending the time window over which it is observable. Rubin's rapid cadence and advanced data processing pipelines will also improve the ability to link fast-moving objects across multiple observations, reducing losses due to motion and noise. Equally important is Rubin's sensitivity to non-ecliptic regions. Its survey strategy does not focus narrowly on the plane of the solar system, making it far better suited to detecting objects arriving from arbitrary directions, including near the solar apex. Simulations incorporating Rubin's capabilities predict a dramatic increase in interstellar object detections. Conservative estimates suggest that Rubin could detect several interstellar objects per year, spanning a range of sizes and activity levels. Some may resemble Borisov, others may resemble Oumuamua, and some may exhibit entirely new behaviours. This shift from single detections to a statistical sample is transformative. With multiple detections, it becomes possible to measure size distributions, velocity distributions, compositional diversity, and activity fractions. Population estimates will no longer rely on extrapolations from one or two objects. Instead, they will be constrained directly by data. Rubin will not eliminate all detection biases. Objects arriving very close to the Sun will remain difficult to observe from Earth, and the smallest bodies will still evade detection. However, it will push these limits far enough that interstellar objects become a routine rather than exceptional observational category. In retrospect, Oumuamua's late detection should not be seen as surprising or unfortunate. It should be seen as expected. It revealed not only the existence of interstellar objects, but also the extent of what current surveys cannot see. Its discovery highlighted the narrow observational window through which such objects are visible, and underscored how much of the interstellar population passes through the solar system unnoticed. The implication is clear. The solar system is continually intersected by material from other planetary systems. We have only just acquired the tools to notice. As survey capabilities improve, missed visitors will become fewer, detection statistics will stabilize, and the study of interstellar objects will move from anecdote to population science. Oumuamua was not late because it was unusual. It was late because our eyes were not yet wide enough open. By the time Oumuamua exited the solar system, it had already altered astronomy in a permanent way, not because it defied physical explanation, but because it forced the expansion of existing frameworks. Before its detection, interstellar objects were an expected but unobserved consequence of planet formation theory. After its detection, they became an empirical reality, subject to measurement, classification, and statistical analysis. The most immediate change was categorical. Oumuamua established interstellar objects as a distinct observational class. Prior to 2017, small bodies were divided into asteroids, comets, centaurs, and trans-Neptunian objects, all defined by orbits bound to the Sun. Oumuamua did not fit into any of these categories. Its orbit alone required a new designation, marking the first time that an object's classification was defined not by composition or activity, but by origin outside the solar system. This distinction matters because origin constrains physics. Bound solar system bodies evolve under repeated solar heating, planetary encounters, and collisional processing within a shared environment. Interstellar objects do not. They experience ejection, long-term isolation, galactic radiation fields, and dynamical mixing over timescales that far exceed those of most solar system processes. As a result, they sample regions of parameter space that solar system objects rarely occupy. Once this was recognized, many of Oumuamua's unusual properties became less surprising. Its extreme shape, tumbling rotation, surface processing, and non-gravitational acceleration all lie at the edge of what is commonly observed among solar system bodies. But none of these properties violate known physics. They instead reflect boundary conditions that had not previously been tested observationally. Interstellar objects are not expected to resemble typical asteroids or comets because they are not typical asteroids or comets. From the standpoint of planetary system formation, Oumuamua provided a long-sought empirical constraint. For decades, numerical simulations had predicted that planet formation is inefficient. A significant fraction of solid material is expected to be scattered outward and ejected entirely during the growth and migration of planets. These predictions were robust but indirect. They relied on dynamical arguments rather than observational confirmation. Oumuamua confirmed that ejection is not just possible, but effective. Its detection implies that the Milky Way contains a substantial population of small bodies that originated in other planetary systems. This in turn places quantitative constraints on how much material typical systems must eject. Even conservative estimates suggest that ejection of solid material is not a minor byproduct of planet formation, but a dominant outcome. This has implications beyond small bodies. If planetary systems routinely eject large amounts of material, then the architectures observed in exoplanet surveys, giant planet migration, eccentric orbits, resonant chains, are not just dynamical curiosities. They are mechanisms that shape the mass budget of planetary systems and populate interstellar space with debris. In this context, Oumuamua is not an anomaly. It is evidence that the solar system behaves similarly to other systems. The Sun has ejected vast numbers of objects over its lifetime. Other stars have done the same. Interstellar space is therefore not empty, but filled with the byproducts of planet formation occurring across billions of stars and billions of years. One of the most persistent misunderstandings surrounding Oumuamua was the idea that its unexplained properties required extraordinary explanations. This interpretation confuses incompleteness with impossibility. In planetary science, it is common to encounter objects that challenge existing models. The response is not to abandon physical law, but to refine assumptions. Oumuamua did not violate conservation laws, orbital mechanics, thermodynamics, or material physics. Every observed property lies within regimes that are theoretically accessible, even if rarely sampled. The non-gravitational acceleration, in particular, was often mischaracterized. Such accelerations are routinely observed in comets. The difficulty was not the presence of an extra force, but the absence of familiar signatures associated with known mechanisms. This narrowed the range of plausible explanations, but did not eliminate natural ones. Crucially, invoking extraordinary explanations is not justified by unexplained details alone. Scientific inference requires weighing prior probabilities. Given that planet formation is known to eject vast numbers of objects, and that surface processing in interstellar space is poorly constrained observationally, the prior probability of an unusual but natural object is far higher than that of an artificial one. Oumuamua did not demand a revision of physics, it demanded better statistics. This is a recurring theme in astronomy. Singular discoveries often appear anomalous until larger samples are available. The second interstellar object, 2I Borisov, immediately demonstrated that interstellar objects can also look completely familiar. Together, the two objects bracket a range of behaviors rather than defining an exception. As more interstellar objects are detected, the properties that once seemed extraordinary are likely to become contextualized within a broader distribution. Perhaps the most lasting change brought by Oumuamua is conceptual rather than technical. Before its discovery, the solar system was often treated as a closed laboratory. Material exchange with interstellar space was considered primarily in terms of gas and dust. Oumuamua demonstrated that solid bodies also participate in this exchange. Planetary systems are not isolated units. They shed material into the galaxy, and they intercept material shed by others. This reframes planetary systems as nodes in a galactic ecosystem. Over cosmic time, solids formed around one star can pass through the gravitational domain of another. While Oumuamua did not interact strongly with the solar system, the possibility exists in principle for such objects to be temporarily captured, to impact planets, or to exchange material across stellar boundaries. The probabilities are low, but the timescales are long. In this sense, Oumuamua blurred a conceptual boundary. It showed that the distinction between extrasolar and solar system material is not absolute. The galaxy is dynamically mixed. Planetary systems contribute to and sample from a shared reservoir of debris. For humanity, the significance lies not in novelty, but in perspective. Oumuamua was not a messenger in any symbolic sense. It was a measurable object obeying gravity, thermodynamics, and material physics. But its mere passage demonstrated that the solar system is embedded in a larger active environment shaped by countless other planetary systems. The first interstellar object ever detected did not arrive with answers. It arrived with constraints. It constrained how planetary systems form, how efficiently they eject material, how surfaces evolve over extreme timescales, and how incomplete current surveys still are. It exposed gaps in observational coverage and motivated the development of new facilities designed to address them. Most importantly, it marked the transition of interstellar objects from theoretical expectation to observational science. From that point forward, the question was no longer whether such objects exist, but how many there are, how diverse they are, and what they can tell us about planetary systems we cannot observe directly. Oumuamua did not change physics, it changed context, and in astronomy, expanding context is often the most powerful transformation of all.